All right, in this video, we're going to be taking a look at related rates problems. We're going to be doing a quick review and giving you the 3 key steps you need to solve any related rates problem. So let's start off with a problem right here. A snowball melts at a rate of 5 centimeters cubed per minute. How fast will the radius of the snowball change when its radius is 10 centimeters? Now, our very first key step is going to be to locate all the rates of change. Now, these rates of change are identifiable by the word rate, or change, or increasing, decreasing, or even the units themselves. So whenever you see a unit of something per minute, per second, per hour, so in this case, 5 centimeters cubed per minute, that's really telling you about a rate of change. Now, you can also use that unit to help you identify what's changing at that rate. So in this case, centimeters cubed is a unit of volume, and that makes sense. Snowballs have volume to them. So my dV dt is equal to 5 centimeters cubed per minute. But the other thing is that this snowball is melting, so that means that the volume is actually getting smaller, so we actually need to put a negative in front of this 5 centimeters cubed per minute. All right. Now, the other rate of change that you always see in a related rate problem is the question itself. So how fast will the radius change? So the question of a related rate problem is always in terms of a rate of change. So radius, dr, or again, dt. Every problem on related rates is going to be ddt. Okay? All right, so I don't know what dr dt is, so I'm going to say dr dt is equal to question mark. All right, now our second key step of solving any related rate problem is to look at the variables that are changing and find an expression that relates those 2 variables together, or maybe 3 variables or 4 variables if you have a really complicated problem. So here, it's volume and radius, and this is a known formula. So we can just look up the formula for the volume of a ball or the volume of a sphere, and we'll see that it's 4/3 pi r cubed. All right, so that's our second key step, is to just put the variables that are changing in an expression that relates them together. Okay. Now, the third key step is to take the derivative of this expression with respect to time. Okay. Now, all of these derivatives are going to be with respect to time. And again, you can tell that by the units, the per second, per minute. That tells you the bottom expression changing is time. All right, now when we take these derivatives, we got to remember to tack on our chain rules. So for example, the derivative of volume, the derivative of just x, or derivative of v is just 1. But anytime you take the derivative of a variable now, we need to tack on a d variable dt. So in this case, dv dt. Okay, on the right-hand side, 4/3 pi r cubed, well, the 4/3 pi, that's just a constant, so it sits there. And then we just do our power rule. The derivative of r cubed is 3r squared. And again, we just took the derivative of a variable, so we're going to tack on dr dt. All right, now the last thing that we're going to do is we're just going to plug in the known information. So for example, on this one, I took the time to write down that dv dt is equal to -5. So we're just going to have 1 times -5, or just -5 on the left-hand side. On the right, we'll have 4/3 pi times 3r squared. The 3's are going to cancel. We're going to get 4 pi. And then r squared, we're just going to look back in the problem, and r is equal to 10. So we'll plug that in. Okay. And then we're left with dr dt, and that's what we're trying to figure out what it is. All right, so now all we have to do is solve for dr dt. So we'll do that up here. Dr dt is equal to the -5 on the left, divided by 4 times pi times 10 squared, and if we multiply all that out, it'll be 400 pi. Okay, so this would be an exact answer. We could simplify if we need to, or if we were plugging into, say, MyLab or something like that, we could plug it into our calculator and round to the correct decimals. Always pay attention to what MyLab tells you on the decimals. Okay, and again, this is dr dt. And the last thing is the units. Well, we can just look at our derivative to tell you what the units are. So dr is a unit of radius, which is centimeters, And dt on this problem is a unit of time, so that's per minute. Okay, so our final answer is -5/400 pi centimeters per minute. Now, why the negative? Well, if the snowball is melting, then it'll be getting smaller, so the radius should be decreasing. All right, before we move on to another related rate problem, let's take a look at the 3 key steps in solving these types of problems. And we'll take a couple notes along the way. So step number 1 is to identify rates of change and express as derivatives. So if you're reading the problem and it says the radius is changing at a certain rate, we would want to write that down as a dr, and all the derivatives in this section are with respect to t, so something like dr dt. Now the other thing to remember is that the units themselves can kind of give away what is changing. So for example, if I see a unit, say 5 feet squared per second, okay, again the per second is a dt, so that goes on the bottom, and feet squared, that's a unit of area. So this might be telling me that the area is changing with respect to time. Okay. So the other key thing to remember about expressing rates of change is that the question itself will always be a rate of change. So for example, if it says, how fast is the width changing? Okay, then that is a rate of change. That is a width, so dw maybe for width. And again, everything is with respect to time. So dw, dt, and again, that's the question that's being asked, say, in this problem. Okay, so that is step number 1, to identify all the rates of change in the problem and express them as derivatives with respect to time. All right, step number 2 on solving a related rate problem is to find an expression relating to the variables which are changing. Okay, so if the problem is telling you how fast the radius is changing and wants to know how fast, say, the area is changing, say of a circle, then we would just want to find the area of a circle formula and say a is equal to pi r squared. Okay, now sometimes it's as simple as that, but step number 2 is really where a lot of the difficulty in related rate problems can come in, because a lot of times you're going to need to use substitution to get the expression down to just the variables that are changing. And I'll have some videos about that in the future. Okay? Now, one other thing that we want to account for in step number 2 is that if something is not changing, then we don't want to put a variable in for it. So for example, if it says that the width is equal to 5 centimeters, but the width is never changing, then we never want to use a w for width there. We just want to put in that fixed amount that's sitting there. Okay? If we put in extra variables on things that aren't changing, it will overcomplicate the problem. So we want to make sure that only things that are changing have variables in this expression. All right, and our final key step on solving any related rate problem is to take the derivative of your formula with respect to t and fill in the known information. Now the key note you need to take here is that when you're taking these derivatives, you're going to follow all the normal derivative rules, but you have to remember to tack on your chain rule, in particular with the ddt. So for example, let's say we had an equation that said y squared is equal to sine of x, and we want to take the derivative of this with respect to time. And remember, every related rate problem is with respect to time. We would follow our normal power rules on the left-hand side. So the derivative of y squared is 2y, but we just took the derivative of a y term, so we need to tack on dy dt. Okay. Similarly, on the right-hand side, the derivative of sine of x is cosine of x, and then taking the derivative of the x inside of there, we need to tack on a dx dt. Okay. From here, we would just plug in whatever information was given in the problem for x and y, and for the change of y or the change of x, and solve for the rate of change that they're asking for. All right, let's take a look at another related rate problem, a little bit harder than our first problem with the snowball. Now, of course, at any point you feel like it, you can pause the video and try the problem yourself, and then unpause it when you're ready to see the solution. All right, so let's start off by reading this problem. A rectangular box has a fixed height of 2 feet, while the length of the box is increasing at a rate of 3 feet per second, and the width of the box is decreasing at a rate of 1 foot per second. How fast is the volume of the box changing when the length is 10 feet and the width is 5 feet? So again, the very first thing I want to do is locate any rates of change in the problem. And again, these are identifiable by the units. The 3 feet per second is the length increasing. So I could write that down as dl dt, and again, all of our derivatives are with respect to time, is equal to 3 feet per second. Okay. On the other hand, the width is decreasing at a rate of 1 feet per second. So I might write that as dw dt, the change in the width per time, is equal to 1 feet per second. But because it's decreasing or getting smaller, I need to use a negative on that unit. All right, and then the last thing is that any of the questions is always a rate of change. So how fast is the volume changing? So we would want to write that as dv dt is equal to question mark. All right, so now our goal is to find a formula which relates these variables together: volume, length, and width of a box. Well, a box has a formula. Volume is equal to length times width times height. Okay. Now, when you're finding this expression, if something is not changing, we want to make sure that we don't put in a variable for it. So in this problem, the height isn't changing. It says it has a fixed height of 2 feet. So I want to substitute into this formula 2 for h. So I'll get volume is equal to length times width times 2, or volume is equal to 2lw. All right, so this is an expression that just relates together the variables which are changing in this problem. All right, so now our last key step is to take the derivative of this with respect to time. And we want to follow all of our normal derivative rules when we do this. We just need to tack on our chain rules whenever we take the derivative of a variable. So on the left, it's pretty easy. It's very similar to the snowball problem. It's just dv dt. Okay. On the right, we have 2l times w. So I said times there because that implies that we need to use the product rule. So we're going to take the derivative of this, thinking of 2l as our first term and w as our second term. So the product rule says take the derivative of the first term, so 2l would be 2, and then the derivative l is dl dt, and then leave your other variable alone, so just w. Okay. Now we're going to add on, leaving 2l alone, and then taking the derivative of w. And now again, you might say the derivative of w is just 1, but we need to remember to tack on dw dt. Okay. All right, so now we're just going to solve for what it's asking for, dv dt, by plugging in all the known information. So for example, we got 2 dl dt was given as 3 feet per second. Okay. The width, I can go back into the problem. Where's the width? The width is 5 feet. So 5n for w. Then 2l, the length of this box is 10 feet, so I'm going to plug in 10 for L. And then dw dt, I need to plug in -1. Remember negative because it was decreasing. All right, from here, we just need to do this arithmetic. So dv dt is equal to, we have 2 times 3 times 5, that's 30. Okay, and then 2 times 10 times -1 is -20. So in total, 30 minus 20, or 10. Okay, and then the units on this is the unit of volume in terms of feet would be feet cubed. Okay, and a unit of time in this problem is per second. Okay, so let's jump right into it. In this problem, we have the Goodyear blimp flying due east at 16 miles per hour at a constant altitude of 2 miles. If the blimp flies over a stadium at noon, then how fast is the distance between the blimp and the stadium changing at 12:15 p.m.? Okay, so in our related rates video that I posted before, I said there's 3 key steps. And the first key step on a related rate problem is to identify the rates of change. And again, these are identifiable by the units a lot of the times. So for example, meters per second is a rate of change. And in this problem, we don't have meters per second, but we have miles per hour. So I see 16 miles per hour. I know that that's a rate of change that I'm going to have to write down in a little bit. Secondly, a related rate problem, the question itself is always a rate of change. So in this one, how fast is the distance between the blimp and the stadium changing? Well, that's a rate of change, a dx dt or something like that. Now this problem doesn't talk about volumes or widths or anything like that, so typically the best way to assign a variable on a problem like this is to draw a little picture. So I'm going to draw a picture. You don't have to be a great artist, so I'm just going to draw a little box for my stadium, and my blimp flies over the stadium at noon, and it's flying at 16 miles per hour to the east. Okay, and really what I want is the picture at the time that it's asking the question. So it asks the question at 12:15 p.m. So I really want to know that the blimp is over here, a little bit to the east at 12:15 p.m. And that's where I want to kind of draw my picture of what's going on. Okay, so it's asking about the distance between the blimp and the stadium. And I'm just going to draw a line connecting the blimp and the stadium together. So it's asking about that distance there. Okay, and I can assign a variable right here to the picture. Now typically I don't like to use d's for distance on these types of problems because you'll be taking derivatives. So you'll have things like dd, dt, and it just looks weird and sounds weird when you say it. So I typically assign a z for a distance in this problem like this. Okay, now what else do we have? Well, we have the vertical height, the altitude, which is always the same. And remember, when you're doing a problem in related rates and something is not changing, don't assign a variable to it. So I just want to put in 2 miles there. Okay, and then the last side is, well, just how far east this blimp is going, and I'll call that x. Okay, so going back into the problem, it says that the blimp is flying due east at 16 miles per hour. Okay, so that means that x is changing, dx dt is changing at 16 miles per hour. Okay, the other rate of change that it's asking about is how fast is the distance between the blimp and the stadium changing at 12:15. So it's asking us how fast dz dt. Remember, all your derivatives are with respect to time in related rate problems. All right, so these are the only 2 variables that are changing in the problem that are being asked about. So what I want to do is find a formula that relates these 2 variables together. Okay, now when you're talking about distance, there are typically 2 ways to do it. You can either use the distance formula if you're on the xy plane, which we're not, or you can typically use Pythagorean's formula. And in this case, there is a little right triangle formed by the blimp at noon, okay, the blimp at 12:15, and the stadium. So we can use Pythagorean's formula to say that z squared is equal to x squared plus 2 squared. Or simplifying, z squared is equal to x squared plus 4. Okay, so now I have a formula that relates together the variables that are changing in the problem. And now the third key step is just to take the derivative with respect to time. Now, remember, when you're taking this derivative with respect to time, you're going to have to use the chain rule. So you'll use your normal power rules. For example, the derivative z squared is 2z, but whenever you take the derivative of a variable, you're going to tack on dz or dx or dy dt. Okay? On the other side, the derivative x squared is 2x, and again, we need to tack on dx dt. Okay? Finally, the derivative 4 is just 0, which you don't have to write, but I will write there plus 0 just so you see where it went. Okay, so now it's asking us what is dz dt. So in order to solve that, I just need to figure out everything else. Well, it already told me what dx dt is. Okay, 2 is just a number in this expression, so I need to figure out what z and x are. So we'll have to do a little bit of side work on this problem. Okay, so if we look back at the problem, at 12 p.m., the blimp was right over the stadium, and the question is asking us about 12:15. Okay? So how far would x be if you flew from 12 to 12:15 at 16 miles per hour? Well, we can use the distance formula. Distance is equal to velocity times time. We know that the velocity is 16 miles per hour, and the time is 15 minutes, or 15/60ths, or 1/4 of an hour. So we're going to have 16 times 1/4, or 4. Okay, so that's going to give us what x is. Okay, so now we need to figure out what z is. Well, remember that z and x are related together by Pythagorean's formula in this problem. So z squared is equal to x squared, which is 4, plus 4. So 4 squared plus 4. So z squared is equal to 20, or z is equal to the square root of 20. Okay. All right, so now we have all the pieces we need to figure out what dz dt is. Okay, so going back to our derivative that we took, we have 2z, so 2 times the square root of 20, times dz dt, okay, is equal to 2x. X we calculated to be 4, times dx dt. Okay, and again, dx dt is 2 times 4, and dx dt, we already wrote that down to be 16. Okay, so overall we can solve this pretty easily for dz dt just by dividing. So we'll have dz dt is equal to 2 times 4 times 16 all over 2 times the square root of 20. Okay, so now it's just calculator time. We throw this all into our calculator, and we'll get approximately 14.3 miles per hour are the units in distance changing in this problem. All right, in this video, we're going to do a related rates problem using the distance formula. So let's jump right into it with an example. So a bug crawls along a path shaped like the curve y is equal to the square root of x, where y and x are both measured in inches. If the x-coordinate of the bug's position increases at 2 inches per second, then find how quickly the distance between the bug and the point 20 is changing when the bug is at the point 4,2. Alright, so the first key step in solving any related rate problem is to identify any rates of change in the given problem. So again, we can identify these with rates of change like inches per second. So it says the bug's x-coordinate is increasing at 2 inches per second. So we can write that as a derivative as dx dt is equal to 2 inches per second. All right, I don't see any other units like that, inches per second, but the question itself in a related rate problem is usually a rate of change, and that's what we're trying to find. So it's asking how quickly the distance between the bug and the point 20 is changing. Okay, so it's a change in distance, so I could write dd dt, or I'm going to use z for my distance, so dz dt is equal to question mark. All right, so that's the first key step, is to locate all the rates of change in the given problem, including the question itself. All right, so now that we found our rates of change in the given problem, our next step is to find some type of equation or expression that relates these variables together. So in this problem, we have x, like an x-coordinate, and z for a distance. And there is a formula that relates them. It's called the distance formula. So all we have to do is look that up, and it says that the distance, I'm calling that z, is equal to the square root of x2 minus x1 all squared plus y2 minus y1 all squared. Okay. All right, now when we find this expression, we want to make sure that things that aren't changing are fixed in this problem, or that we have too many variables underneath here right now. So for example, it's asking us how quickly the distance to the point 20 is changing, but that point 20 is not changing at all, so we can plug that into this distance formula, and we can start to simplify it. So we get z is equal to the square root of x minus 2 squared, and I no longer need that x sub 2 because I don't have two x's anymore, and then plus y minus 0 squared. All right, so now we have a little bit simpler distance formula, but we can go a little bit further, because if you look at the problem, it only tells you about how quickly x is changing, and it asks you how quickly z is changing. It doesn't ask about y at all, so we really don't want this in this expression. So we can do a little substitution, namely, in this problem, we know that y is equal to the square root of x. So we can substitute that in, y is equal to the square root of x, and then we get an expression that only relates to things that are changing in the problem that we care about. Okay, so it tells us about dx dt, and it asks us about dz dt. So those are really the only things we care about. So we're going to plug that in, and we'll end up with z is equal to the square root of x minus 2 all squared plus, and when we plug in y is equal to the square root of x, we'll get the square root of x all squared, and this will all simplify down to z is equal to the square root of x minus 2 all squared plus x. So that's step number 2 in our key steps of doing a related rate problem. All right, now that we found an expression that relates together the two variables which are changing in this specific problem, our third and final key step is to take the derivative with respect to t using implicit differentiation. So again, we're going to always take derivatives with respect to time in these related rate problems. And when we do this, we just need to remember to tack on those dz dt's, dx dt's whenever we take the derivative of a variable. So for example, on the left-hand side, we need to just have dz dt. That's the derivative of z with respect to time. On the right-hand side, it's a little bit more complicated. We're going to need a couple chain rules here, but we're going to start with the outermost function, which is the square root. And the derivative of square root in general is that it sends two square roots down to the bottom. And whatever's inside the square root just remains the same. So x minus 2 all squared plus x. Then on the top, we want to put the derivative of the inside. So we'll start with the derivative of x minus 2 all squared. Using a chain rule, that's 2 times x minus 2 to the first, and then times the derivative of the inside. Now the derivative of the inside would normally just be 1, but remember we just hit a derivative of x and we need to tack on dx dt. All right, so that's the derivative of that first term. The derivative of the second term is the derivative of x. Again, it's not 1 in this case, it's dx dt. Okay, and that's all the hard part. Now all we have to do is plug in the given information and then simplify. All right, so after finding this derivative, all we have left is to plug in the given information and simplify it down. So to figure out what dz dt is, we need to know what x is. Well, we're figuring out where is this bug at this time, and it is at 4, 2. Specifically, it's at x is equal to 4. Okay, we already circled off that dx dt is equal to 2 inches per second. So now we just need to plug these numbers in. So dz dt is equal to 2 times x minus 2 is 4 minus 2 times dx dt is 2 plus dx dt is again 2, and that's all over 2 times the square root of x minus 2 squared, so that'll become 4 minus 2 squared, and then plus another x, so plus another 4 under our square root. All right, so this is all just arithmetic, and we can calculate all these numbers. On the top, if we multiply and add all those numbers, we're going to get 10. On the bottom, we're going to get 2. And then underneath the square, if you did all that simplification, we get 4 minus 2 is 2 squared, plus another 4, so the square root of 8. Okay, now this can be simplified as a fraction, but again, it depends on the problem on exactly what you want to do. Let's say that we want to round this to 2 decimals, then this is going to be 1.77. Okay, just plugging into the calculator. And then our units. The units of z is the units of distance in this problem, which is inches. And dt is the unit of time in this problem, is per second. Okay, so that's how we solve a related rate problem using the distance formula. Again, we just use the given formula, the distance formula, we write it down, and then we're just going to plug in the information from the given problem, only using the variables that are important in the problem that they ask about or they tell us about that is changing. Okay. Alright, in this video we're going to be taking a look at another related rate problem, this time involving distance between ships. So at noon, ship A sails from a dock at 10 miles per hour. Ship B is sailing west at 15 miles per hour and will reach the dock at 3 p.m. How fast will the distance between the two ships be changing at 2 p.m.? Okay, now that we've read the problem, our first key step in solving it is to locate any rates of change and express those as derivatives. So in this problem, it says that ship A is sailing north at 10 miles per hour. That 10 miles per hour is a rate of change, and we're going to express that as dA dt is equal to 10 miles per hour. Okay, ship B is also sailing. It's at 15 miles per hour, so I'm going to represent that as dB dt is equal to 15 miles per hour. And finally, the question in a related rate problem is always a rate of change as well. So how fast is the distance changing? I'm going to call that dz, z for distance, so dz dt, and that's our question in this one. Okay, so again, that is our first key step, is to locate the rate of change and just express them as derivatives and just write them down. Okay, after we found our rates of change, our next key step is to find a expression which relates together the variables that are changing. So in this case, A, B, and Z, the distance between the two ships. Now in this particular case, it's good to draw a picture. And when you're drawing a picture when things are changing, you really want the picture at the time that they're asking about. And here, they're asking about at 2 p.m. So we want to draw a picture of what this scenario is going to look like at 2 p.m. So we have a dock. I'm going to label that D. And then ship A sails north from the dock. It leaves at noon, and it's going 10 miles per hour. So at 2 p.m., how far along north will it have gone? Well, 2 times 10 miles per hour is 20 miles. So it would have gone 20 miles. But this side is still changing, so we want to put a variable there. I'll call it A. All right, now that we've figured out where ship A is, let's figure out where ship B is at 2 p.m. Well, it doesn't reach the dock until 3 p.m. and it's sailing west, which means at 2 p.m. it would still be east of the dock. Okay, so it'll be over here somewhere. Okay, and it takes 1 more hour from 2 p.m. to 3 p.m. for it reaching the dock, and it's going 15 miles per hour. So in that 1 hour, it has to travel 15 miles. Now that side is changing, so I need a variable there. So I'm going to call that B for the distance that B needs to go. Okay. Now you'll notice that B is decreasing as the ship sails towards the dock. So since that side is decreasing, I need to go back and change my rate of change. dB dt is not positive 15 because it's getting smaller. I need it to be negative 15 miles per hour. Okay, so now the final thing that we need is just the distance between these two ships, which is Z. I've already called it Z. Okay, and now I just need the relationship between A, B, and Z. And typically when we're doing distance problems, the relationship that you use is either going to be the distance formula if you're on an XY plane, or in this case, when we're talking about ships in the sea, we're going to use Pythagorean's theorem. So we have that Z squared is equal to A squared plus B squared. Okay, and that's our second key step, is to get a relationship between the variables which are changing in this problem. In this problem, it's A, B, and Z. Okay, now that I found the relationship between the variables that are changing in the problem, I'm going to take my third key step and I'm going to take the derivative of this with respect to time. So d dt of this entire equation. All right, now remember, when you're taking this derivative, you have to remember to use implicit differentiation, or the chain rule, and tack on your dz dt's, dA dt's, dB dt's. So in this case, it's just some power rules. The derivative z squared is 2z, and then we tack on our chain rule, dz dt. Okay. On the other side, we have 2a for the derivative of a squared, but we have to tack on dA dt. Again, anytime you take the derivative of a variable, you tack on the variable dt. Our last derivative is b squared, becomes 2b, and then dB dt. Okay. All right, after we've taken the derivative, all we need to do is plug in the given information and solve for the variable that it's asking for. Now the first thing I'm going to notice is there's a bunch of 2's in this equation. I can divide both sides by 2 and cancel all those things out. Okay, now in order to solve this, I need to figure out what z is. Now the thing that can tell me what z is actually the thing that I differentiated in the first place. I know that z squared is equal to a squared plus b squared. So that means that z squared at 2 p.m. is equal to a squared. Well, a is 20, so 20 squared, plus b squared, and b at 2 p.m. is 15, so plus 15 squared. So z squared is equal to 20 squared plus 15 squared. If we do that arithmetic, we'll get z is equal to 25. All right, so now we can plug in everything that we know and solve. So z is 25, so 25 dz dt is equal to a is 20, dA dt is 10, plus b in this problem is 15 at 2 p.m., and dB dt is equal to negative 15. Okay, or we get 25 dz dt is equal to 200 minus 225 when we do this multiplication, or 25 dz dt is equal to negative 25. So that's a pretty easy division to do. dz dt is equal to negative 1, or 25 divided by 25, and the units on this is miles per hour for the distance. The angle of elevation of the sun is decreasing at a rate of 0.25 radians per hour. How fast is the shadow cast by a 400-foot tall building increasing when the angle of elevation of the sun is pi over 6? Alright, now that we've read the problem, our first key step in solving it is to find any rates of change and express those as derivatives. So for example, at the very beginning of the problem, this one says that the angle of elevation is decreasing at a rate of 0.25 radians per hour. Now, the units themselves tell you that that is a rate of change, and we can express this as the change in theta, the change in the angle, over a change in time, is equal to negative, because it's decreasing, 0.25 radians per hour. Okay, now there's no other units like that in this problem, like something per hour or something per second, but the question itself is always a derivative in these related rate problems. So how fast the shadow is increasing, we can express that as ds, the change in the shadow's length, over dt is equal to question mark. So that's what we're looking for. So those are all the rates of change either told about in this problem or asked about in this problem. And again, that's the first key step in solving a related rate problem. Okay, our second key step in solving a related rate problem is to find an expression that relates together the variables which are changing in the problem. So in this case, the angle theta and the length s of the shadow. Now when we're dealing with angles, a lot of times the best strategy to do this is to draw a picture. So here we have a 400-foot tall building. We have the sun up in the sky, and the sun's rays hit the top of the building and cast a shadow along the ground. Now the length of the shadow, it's changing as the sun sets. We'll call this S, okay? And the angle that that shadow makes with the sun, call that the angle of elevation, and we're going to call that theta. All right, so now we need some type of trig function that relates together these things given in this problem. So the angle theta, now the height of the building is across from that, or the opposite side, and the length of the shadow is adjacent to that, or right next to it. So the trig function that has opposites and adjacents in it is tangent. So namely, we have tangent of theta is equal to the opposite side, 400, over the adjacent side, s. Okay, so now this is an expression that deals together with the angle theta and the length of the shadow, s. But we can simplify this a little bit, and it'll make our lives a little bit easier when we do our next step of taking the derivative. Namely, since I'm trying to figure out ds dt, it would be nice if s was by itself and not in the denominator of a fraction. So I can do this by just cross multiplying, and we'll get s times tangent of theta is equal to 400. And then to avoid a product rule, I'll divide both sides by tangent. We get s is equal to 400 over tangent. And the nice thing about having tangent in the denominator is that it just turns into the reciprocal of tangent, which is just another trig function. And we know that that is cotangent. Okay, so there is a relationship between the length of the shadow S and the angle theta of elevation. Okay. All right, our final key step in solving a related rate problem is to take our derivative with respect to time using implicit differentiation and chain rules as they come across. So we're going to take the derivative of the entire expression with respect to time. So the derivative s, again, is just 1, but then anytime you take the derivative of any variable in a related rate problem, we need to tack on d variable dt, so in this case, ds dt. Okay, so that's why I put s by itself. So now it's just already solved for ds dt, and that's what we're looking for. Okay. Now the derivative of the other side, the 400 just sits there. And the derivative of cotangent is negative cosecant squared of theta. And then again, we need to tack on our little chain rule here. The derivative of theta is d theta dt. Okay, our final step here is just to plug in the given information and solve for what it's asking for. So in this case, it's asking for ds dt, and we're already solved for ds dt. And we're just going to plug in the given information. So 400 times negative cosecant squared of the angle is pi over 6. Okay. And then the d theta dt is the negative 0.25 radians per hour that we plugged in at the beginning. Okay. All right, so now this is, we could do this in the calculator, we could use a unit circle, but it's just arithmetic at this point really. So we have 400 times negative, and then cosecant squared of pi over 6, if we threw that into, say, sine, so it's 1 over sine squared of pi over 6, to help us think about it, or to use the calculator, times negative 0.25. Okay, so we'll have 400, and then negative 1 over, and sine of pi over 6, we could use our calculator, unit circle, that's 1/2. So we're going to get 1/2 squared, and then times another negative 0.25 over here. Okay, and now we could use our calculator to do all this, and if we multiply all this stuff out, it's just going to come out to be 400. Okay, now we can look at the derivative itself to think about the units. So ds is a change in the shadow's length, and in this problem, length was measured in feet. And dt was a unit of time, and time in this problem was radians per hour, so time is hours. So the length of the shadow is increasing at 400 feet per hour at this time. A 6-foot tall man is walking at 3 feet per second past a streetlight which is 15 feet tall. How fast is the tip of his shadow moving 2 seconds after he passes under the light? All right. So our first key step on solving any related rate problem is to find the rates of change. And again, a lot of times we can find these by the units. Anytime you have a unit that's per a unit of time, like a feet per second, that is a rate of change that we're going to want to write down in a little bit. Okay. Secondly, a related rate problem, the question itself is always a rate of change. So how fast the tip of a shadow is moving, okay, that is a rate of change that we're going to want to write as a derivative. Okay. Now, because this isn't things like widths or lengths where we could quickly assign a variable like w or l, what we want to do is draw a picture so that we can assign the variables right on the picture. Okay. So what I'm going to do is just draw a light. Okay. It doesn't have to be a fancy picture. Okay. So we have a street light. We have a man who walked past it. Okay. And then the street light's going to cast a light. It's going to hit the top of his head, go down to the ground, and that casts the tip of his shadow. All right. Now, when we're drawing this picture and we start to assign variables, we only want to put variables on things that are changing. So for example, his shadow is growing, so we would want to put an S there for shadow maybe. Okay. He's also walking away from the street lamp. Okay, so we're going to put another variable there. I'm going to just say x, okay, for the distance from the man to the street light. Okay, it also mentions that the street light is 15 feet tall, But that's not changing. The streetlight shouldn't be growing or shrinking in the middle of this problem, so I don't need a variable on that. Same thing with the man. He's 6 feet tall, okay, but he's not growing or shrinking in the middle of the problem either, so we can just label 6 feet. We don't want a variable on that either. Okay, so going back to the rates of change in the problem, it says that the man is walking at 3 feet per second, so that's how quickly x is changing, or dx dt is equal to 3 feet per second. It's asking us about how fast the shadow is moving, so it's asking us what is ds dt. So ds dt is question mark. Okay. Now it's actually not quite asking about that in this problem, which we'll see at the end of the problem, but we'll get to that again at the end. All right, but that's our first key step, is we want to find the rates of change in the problem, and that helps us do the second key step, which is to find an expression or an equation which relates together these variables x and s. All right, and on a shadow problem, the typical way to do this is with similar triangles. We'll notice that the man and his shadow is forming one triangle, and that's sitting inside of the triangle formed by the streetlight all the way to the tip of his shadow. Okay? Since they're sitting inside of each other, they're called similar triangles. So the sides are in proportion to each other. So for example, for the blue triangle with the man and his shadow, on the ground, s over the man's height, 6, is in the same proportion as the big red triangle. Well, along the ground is x plus s, and in place of the man's height, instead of that, on that side is 15. Okay, so this is an expression which relates together the two variables x and s. And one thing about these expressions is you can simplify before you take a derivative. So I can cross multiply here. So 15 times s will give us 15s. And then cross multiply the 6 over to the other side. 6 times x plus s gives us 6x plus 6s. And we can even further simplify it by putting all the s's on one side. So subtract 6s gives us 9s is equal to 6x. And if we wanted to, we could divide both sides by 3 in this particular problem. So 3s is equal to 2x. All right, so now that we have an equation relating together the two variables that are changing in this problem, we can take the derivative with respect to t. Now again, all the derivatives are with respect to t, so when we take these derivatives, we're going to have to use our product rules, our chain rules, our quotient rules, and explicitly implicit differentiation. So when we take the derivative 3s, it's just 3, okay? But then we always have to tack on a ds dt or dx dt, the variable that we're taking the derivative of with respect to time. Okay? On the other side, the derivative 2x, I'm sure you know that, is just 2. But again, anytime we take the derivative of a variable, we need to tack on that implicit differentiation, like a chain rule, dx dt. Okay, so it's asking us what is ds dt, and we know what dx dt is. It's 3, so we can just plug that in and we should be able to solve. Okay, so we got 3 ds dt is equal to 2 times dx dt is 3. Okay, so that means when we divide, ds dt will be equal to just 2 times 3 over 3, or 2 feet per second. Okay, so we solved this problem with similar triangles, and we got excited, and maybe we look in the back of the book and it's the wrong answer, or we type it in MyLab and it's the wrong answer. Okay, so what's going wrong with this is the fact that the shadow is moving because the man is moving as well. So you'll notice that this says that the shadow is moving at 2 feet per second. But the man is already moving at 3 feet per second. So somehow the shadow is moving slower than the man. That doesn't make any sense. The man and the shadow are attached. So actually, how fast the shadow is moving, we have to add these two things together, because the shadow is growing at 2 feet per second, plus it's moving at 3 feet per second because it's moving with the person that's casting the shadow. So we end up with a total of 5 feet per second. A water tank is in the shape of an inverted cone whose height is 5 meters and has a radius at the top of 3 meters. If water is flowing out of the cone at 1 meter cubed per minute, then find the rate at which the water level is changing when the water is 2 meters deep. Alright, remember that our first key step in solving any related rate problem is to find the rates of change within the problem. Again, we can identify these by rates of change. They say change, increasing, decreasing, or simply by the units themselves. So right here I see a 1 meters cubed per minute. Okay, and I can write that down, 1 meters cubed per minute. And again, I can use the units themselves to kind of tell me what my derivative is. Meters cubed on the top, that's a unit of volume. So this should be a change in volume. And per minute is a unit of time. So dV dt. Now if we read a little bit closer, it says the water is flowing out. So that means that my volume is changing in a negative manner, that the volume is getting less. So I need to put a negative 1 meter cubed per minute. So my change of volume per unit of time is negative 1 meters cubed per minute. All right, now the question itself in a related rate problem is also a rate of change. It's asking at what rate is the water level changing, okay? So for the water level here, it's talking about the height of the water because we're talking about a cone going up and down. So I'm gonna say that dH dt is equal to question mark. All right, so these are the only two rates of change that are given in the problem. So I wanna square these off, okay? And then we'll move on to our second key step in a related rate problem. All right, so our second key step in solving a related rate problem is to find a relation between the rates of change in your problem. So this is talking about the volume and the height of the water, which is sitting inside of a cone. And the volume of a cone is a known formula. We can just look that up. It is volume is equal to 1/3 pi r squared times h. All right, so this is an initial equation that we can use. However, if you notice, there's volume which is changing, there's height which is changing, but there's also a radius in there. And the problem doesn't tell us how fast the radius is changing, nor does it ask how fast it's changing. So we really want to get rid of that radius in this equation. And how do we do that? Well, we use the fact that the water is sitting inside of a cone, which they say is initially 5 feet high and has a radius at the top of 3 meters. Okay. And then the water has to sit inside of here at a given radius and a given height. And because it's sitting inside this cone, the radius and the height will be in the same proportion as the outside cone. So we get an equation like r over h is in the same proportion as 3 over 5. And then we can solve this for r by multiplying h over, and we'll get r is equal to 3h over 5. And then we can take that and plug it in for r in our equation for a cone. So 3h over 5 will get plugged into the volume of the cone. All right, so let's do that algebra. We'll get our volume is equal to 1/3 pi. Instead of r, we'll write 3h over 5 all squared times another h. We can simplify this, so we'll get 1/3 pi. We'll square 3h over 5, giving us 9h squared over 25 times another h here. And if we multiply all these numbers out, we'll end up with 3 over 25 pi, and then multiplying our h's, h cubed. So there's an equation that relates together the only things that they ask about or care about in this problem that are changing, volume and height. All right, so our third key step of solving any related rate problem is once we found this equation relating together the volume and the height, we're going to take the derivative of this equation with respect to time. And remember, all of your derivatives in related rate problems are d dt. Now, when we do this, we're just going to apply implicit differentiation, so our normal derivative rules, and anytime we take the derivative of a variable, we're going to tack on that variable dt. So for example, the derivative on the left-hand side, the derivative of v, is just 1, and then dv dt. Okay. On the right-hand side, 3 over 25 pi. Those are just numbers, they just sit there. And the derivative h cubed is 3h squared, and then dh dt. Okay, so there's our derivative, and the final step now is just to plug in all the known values and then simplify and solve. All right, so let's try plugging in these values. dv dt is equal to -1. Okay, 3/25 pi is just 3/25 pi times 3, and then h squared. Let's look through the problem. Where is h? Well, it's the height level of the water, and it says that the water is 2 meters deep when this is occurring. So we're going to plug in 2 for h, and all that leaves us with is dh dt, and remember that's what we're solving for. All right, so now it's just a matter of arithmetic. So we're going to get -1 is equal to, and if we multiply all these numbers together, we're going to get 36 pi over 25 times dh dt. Okay, and then multiplying by the reciprocal to both sides, we'll get that dh dt is equal to -25 over 36 pi. And now we can attach the units, which is going to be the units of height is meters, and the unit of time in this problem is minutes. So there is our final answer. Alright, now if you like this video, please take a moment and like it, and then subscribe to my channel so you can get more math reviews in the future.